As we said previously, rate laws are always determined experimentally. Reaction order is always defined in terms of reactants, not product concentrations, and the order of reactant is not related to the stoichiometric coefficient of the reactant in the balanced chemical equation. Again, fluorine reacting with 2 moles of ClO2 generates 2 moles of FClO2. The rate is equal to K times the concentration of F2 times the concentration of ClO2. Even though there's a 2 in front of the ClO2, it's still first order in ClO2. Zero order reactions. A zero order reaction has the rate equal just to a constant. There is no concentration term. For a first order reaction, the rate is equal to K times the concentration of the reactant. There are 2 types of second order reactions. The rate can be equal to K times the concentration of A times the concentration of B, that is 2 reactants, or the rate is equal to the square of the concentration of A times the rate constant. Let's consider first order reactions. The type of a decomposition, A goes to a product. The rate is going to be equal to minus the change in the concentration of A over the change in time. The rate will be equal to K times the concentration of A. If we want the rate constant, we take the rate and divide it by the concentration of A. The units are going to be 1 over seconds, or seconds to the minus 1. Change in the concentration of A with the change in time is equal to K times the concentration of A. If we integrate this equation, we can get the following. The concentration of A is equal to the initial concentration of A times e to the minus kt. If we plot the concentration of A versus time, it's a hyperbola. But if we plot the log of the concentration of A versus time, we get a straight line whose slope is equal to minus k, and intercept equals the log of the initial concentration of A. The expression is the log of A equals the log of A sub 0 minus kt. Let's look at a first order reaction, the decomposition of 2 moles of N2O5. That yields 4NO2 plus O2. The rate is going to be equal to the concentration of N2O5 times the rate constant. The analytical equation is as follows. Either in the logarithmic form, the concentration of A at any time divided by the concentration initially, the log of that, equals minus kt, or the exponential form of the equation, the concentration at any time equals the concentration initially times e to the minus kt. We will do problems with both these equations. You could also determine k graphically. If we plot the log of N2O5 at any time versus the time, we get that straight line. If we calculate the slope, we get the slope is equal to minus k. In this case, it's 5.7 times 10 to the minus 4 reciprocal seconds. K always has these strange units. The half-life, T1 half, is the time required for the concentration of a reactant to decrease to half of its initial concentration. T1 half equals T when the concentration is 1/2 the original concentration. If we substitute that in, we get a very simple expression. It reduces down to the log of 2 divided by k, or the constant 0.693 divided by k. Remember, ln is natural logarithm. Here's a graphic showing the decrease in a concentration of A with time, decreasing by 1/2 at each half-life. Of course, you never get to 0. Second order reactions. A goes to product. In a second order reaction, the rate is going to be equal to K times the concentration of the reactant A squared. The rate constant can be calculated by taking the rate and dividing it by the square of the concentration of A. Here the units are 1 over molarity times seconds. If we take the expression minus the concentration of A divided by the concentration divided by the change in time, that equals K times A squared. If we integrate this equation, we get the following. It's 1 over the concentration of A equals 1 over the initial concentration of A plus KT. The half-life is given by 1 over K times the initial concentration of A. If we plot 1 over the concentration of A versus time for the second order equation, we get a slope equal to K and an intercept 1 over the initial concentration of A. There's also zero order reactions. A goes to product. In this case, the rate is equal to just the constant. The constant has units of molarity divided by seconds. The change in the concentration of A over the change in time is still equal to K. It's negative because it's a disappearance. The analytical equation is the concentration of A equals the concentration initially minus KT. The half-life is equal to the initial concentration of A divided by 2 times the specific rate constant. If we plot the concentration of A versus time for a zero order reaction, we get a slope equal to minus K and the intercept equals the initial concentration of A. Here's a summary of zero order, first order, and second order reactions. Notice for second order reaction we're taking the simpler one. K equals just the concentration squared.